On the 4th of February, 2023, a patch of storm clouds began to turn, slowly, off the northern coast of Australia. Weather agencies gave it a name, Freddy. Nobody expected much. 5 weeks later, that same storm was still alive. It had crossed an entire ocean, more than 12,000 kilometers of open water, and it was tearing into the coast of Africa. 36 days at sea, longer than any storm ever recorded on this planet. No engine, no fuel tank, nobody at the controls. Your car cannot run for 5 weeks straight. A jet cannot. A power station needs a constant river of coal or gas or uranium. Yet a storm, a thing made of air and water, powered itself for over a month. How? To answer that, you have to stop thinking of a hurricane as weather. You have to start thinking of it as a machine. Every engine on Earth does the same basic job. It takes heat from somewhere hot, turns part of that heat into motion, and dumps the rest somewhere cold. Your car burns fuel at 2,000 degrees and throws the waste heat out of the tailpipe. A power station boils water, spins a turbine, and bleeds the leftovers into a cooling tower. A hurricane does the same job. Its hot side is the surface of a tropical ocean. Its cold side is the edge of space. And its fuel is something you would never think to call fuel: warm seawater. All summer long, the sun pours energy into the tropical sea, day after day, week after week. By late summer, the surface of the Atlantic between Africa and the Caribbean is a ribbon of water at 28, even 29 degrees Celsius, and the warmth runs deep. 50 meters down, the sea can still feel like bathwater. But the ocean does not hand that energy to a storm as heat you could feel. It hands it over in disguise, as vapor. Turning 1 kilogram of seawater into vapor soaks up about 2.4 million joules. That is a microwave oven running flat out for 40 minutes, packed invisibly into a single kilogram of humid air. Physicists call it latent heat, sleeping heat. The vapor carries the sun's energy the way a sealed truck carries cargo, invisible until somebody opens the doors. Trade winds skim across the warm surface and load the lowest kilometer of sky with this charged vapor. Warm, wet, and ready. The fuel is aboard. The engine only needs a spark. The spark is usually small. A cluster of thunderstorms drifting west off the coast of Africa. A ripple in the winds. Air starts to rise. Rising air cools, and cooler air cannot hold its vapor, so the vapor condenses back into cloud droplets. The moment that happens, the sleeping heat wakes up. Condensation pays back every joule that evaporation borrowed. The rising air grows warmer than everything around it, so it rises harder, like a hot air balloon that keeps relighting its own burner. All that air leaving the surface means less air pressing down. The pressure falls, and air from hundreds of kilometers around begins to pour in across the sea to fill the gap. But the Earth is turning underneath. The incoming air cannot fly straight. It bends. And the whole system begins, slowly, to spin. And now comes the trick. The one trick that separates a hurricane from every other storm on this planet. Faster wind over warm water evaporates more vapor. More vapor means more condensation. More condensation means more heat and a deeper fall in pressure. And deeper pressure means faster wind. The storm is feeding itself now. Every lap around that loop makes the next lap stronger. Engineers call it positive feedback. Sailors call it something else. A hurricane being born. Give the loop 3 days over warm water and it builds itself a body. A rotating structure of cloud, hundreds of kilometers across. At the center stands a ring of thunderstorms called the eyewall. This is the combustion chamber. Winds here can pass 250 kilometers per hour, and the air races upward 15 kilometers to the doorstep of the stratosphere. Inside that ring hides the strangest room in the atmosphere. The eye. Here, the air sinks gently and the sky clears. Sailors trapped in the eye have looked up at blue sky and sunshine, while a circular wall of storm surrounded them on every horizon. And at the very top sits the exhaust. The spent air fans out in a great spiral of ice cloud and sheds its leftover warmth into air that sits near minus 70 degrees Celsius. Hot intake below, cold exhaust above. In the 1980s, meteorologist Carrie Emanuel worked out the mathematics. A hurricane runs on the same thermodynamic cycle as a steam engine, the kind Victorian engineers built from iron and rivets. So how much power does this engine actually make? The numbers read like misprints. A mature hurricane condenses enough vapor to drop about 20 billion tons of rain in a single day. Turning that vapor back into water releases roughly 600 terawatts of heat. For scale, human civilization, every power plant, every car, every furnace and phone charger on Earth runs on about 20. One storm. 30 times the power draw of our entire species, built from seawater and sunshine. Nearly all of that energy leaves with the exhaust or falls back out as rain. Less than 1% survives as wind, but that sliver alone roughly matches half the electricity humanity generates, spent blowing in circles over an empty sea. Which brings us back to Freddy. Your car runs dry after a few hundred kilometers. Why does the storm never run out? Because the storm never leaves the fuel depot. The tropical ocean is one continuous tank of warm water wrapping a third of the way around the planet. And a hurricane is a machine built to travel along it, drinking as it goes. A typical storm rides the steering winds at 15 or 20 kilometers per hour, bicycle speed. But that slow roll means every hour brings fresh, warm sea beneath the engine. Every hour, a refill. Keep 3 conditions true, and it simply does not stop. Warm water below, gentle winds aloft, moist air all around. That is how a hurricane named John crossed the entire Pacific in 1994 and stayed alive for 31 days. And that is how Freddy broke every record in 2023. Along the way, it collapsed and reignited 7 separate times, an engine misfiring in the middle of the sea, and catching again and again. But no storm runs forever. 4 things can kill a hurricane, and all 4 are always out there, circling. The first is wind shear. When winds at high altitude blow harder than the winds below, they shove the top of the engine sideways, tilting the chimney until the rising heat spills away from the core. The second is dry air. Deserts exhale over the ocean. When a storm swallows a lungful of dust-dry Saharan air, the vapor line clogs and the burner gutters. The third is the strangest. A hurricane can starve itself. Its own winds churn cold water up from the deep, so it drags a long trail of chilled sea behind it. A cold wake. A storm it stalls ends up parked over the one stretch of ocean it has already drained. And the fourth is land. The moment the eye crosses a coastline, the fuel line is cut. A hurricane can lose half its winds within a day of landfall. The engine starves fast. Land is what finally stopped Freddy. After 36 days at sea, it pushed into Mozambique and Malawi, and the hills wrung it out. The machine that had crossed an ocean came apart over land in less than 2 days. And as it died, it dropped months of rain in a week. The floods took more than 1,000 lives. The engine itself is neither cruel nor kind. It is physics. But what it carries, when it finally reaches the shore, lands on people. Which leaves one last question. Why does the Earth build these machines at all? Because the planet has a bookkeeping problem. The tropics soak up far more sunlight than they can shed. The poles shed far more than they catch. Somewhere, somehow, the surplus heat has to move. Winds carry some of it. Ocean currents carry more. And when the tropical sea has banked too much summer, the atmosphere opens a relief valve. A hurricane is the planet balancing its books. Misplaced summer gathered into a spiral and shipped toward the cold. So the next time you see one from above, a white spiral turning over a dark sea, you will know what you are looking at. A heat engine the size of a country, running exactly as physics demands, on nothing but sunlight and seawater. It asks for no fuel because the sun already paid. It needs no driver because the laws of heat steer it. And it will run for as long as the warm water lasts.